Today, my topic is about the electrifying carbon dioxide into fuels and chemicals. So it's not necessary actually for me to emphasize again the importance of renewable energy technologies, especially for nowadays to combat climate change. With the fast development of clean technology over the past several decades, especially the solar and wind, now we can easily harvest green and cheap electrons especially from solar. As you can see that the price of solar electricity continues to decrease, and the Department of Energy in the U.S. They recently even made a more ambitious goal of directly bring down the futures cost of solar electricity from the 3 cents per kilowatt hour here all the way down to 2 cents per kilowatt hour in 2030, so about 10 years later. So that actually brings us into a new opportunity that in the future we will expect a lot of cheap and clean as well as abundant electrons, and how we're going to use that electrons in the future will become a challenge and opportunity. So our idea is if we can coupling these green resources, the electrons, with accessible molecules, simple molecules that we can easily get from air, such as carbon dioxide, oxygen, water, or nitrogen, and with help of electrocatalysts, if we can store those electric energies into the simple chemical bonds, like the HH bond, like what we can do is split water to clean hydrogen, right? A CH bond, if we can reduce carbon dioxide back into methane and other hydrocarbons, or the NH bond, if we can reduce nitrogen electrochemically to ammonia, so that we can realize a lot of the green synthetic pathway for the chemical feedstocks and fuel feedstocks that we're currently using, as well as for as a very efficient way for energy storage. So among those electrochemical reactions, one of the electrochemical reaction that attracts most of attention is the carbon dioxide reduction, especially in recent years. If you can look at the half-cell reaction, as you can see, the carbon dioxide molecule can combine with electrons and also protons from water, so that you can produce so many different products ranging from C1 like CO methane or methanol, right, to C2 like ethylene, ethanol, and even up to C3 products like N-propanol. And in that case, we can have a far future dream. That is, if in the future, in the next 50 or even 100 years, we can effectively capture all the carbon dioxide we emit and utilize the renewable electricity to convert them back into the chemicals and fuels that we typically use, then we can probably close the carbon loop. That is being said, this might be our future dream, in the next 50 years or so, very far future dream. But if we look into a near future, from a near future's perspective, this carbon dioxide reduction technology might still also receive very strong market driving force. If you look at this simple TA analysis, the blue bar represents the current market price for those chemical feedstocks like carbon monoxide, formic acid, methane, and so on. And this yellow bar represents a techno-economic analysis, simple analysis of the production cost if you produce the exactly same molecules, but not from traditional petrochemistry, but from the CO2 reduction. We do realize that some of the molecules, some of the chemical feedstock like CO and formic acid, they probably will be more efficient and cheaper than the current chemical engineering industry. So that actually provides us a great opportunity and a market driving force to push forward these technologies. But the thing is, this, like what I mentioned, this is a very simple and straightforward techno-economic analysis. And the major driving force is the electricity price can be brought down very, very low, 2 to 3 cents per kilowatt hour. But even though we get the low electricity price, to deliver this cost targets is not that easy. actually, there are still a lot of challenges. For example, we need to have a lot of the performance metric requirements for us to deliver so that we can achieve that eventual price goals. For example, if we need to deliver very high current density, that is an effective way for us to produce large quantities of the chemicals, but in a smaller device. So you can lower down the capital cost. And also, once you deliver such high current densities, you still need to maintain a very good product selectivity. What does that mean? You can see that the CO2 can actually be reduced to so many different products. And in a more industrialization process, you do want your electrons to be delivered to a single product with high selectivity. So more than 90% towards a desired product. By maintaining these two strict and difficult and challenging parameters, we also have the third parameter to deliver, which is the a long-term stability. You want to operate your cell under this high current density and high selectivity, but still maintain a very good stability for at least 1,000 hours. And in some other industrialization requirement, we might need more than 10,000 hours or more. So to deliver those performance targets, by only focusing on the catalytic material design might not be enough. That's the reason why we always focus on both parts, which is to integrate both catalytic material design and reactor engineering. So coupling these two directions together, we probably will have the opportunity to help us to deliver the goal. That is exactly what we have been focusing on over the past several years in my group's research. We're not only focused on the catalytic material design, we design different type of novel nano electrocatalysts to help us to deliver the intrinsic performance. And that has a lot of collaboration with the Canadian light sources, because we want to understand better using the X-ray beams to understand better about our material structures and the electronic properties. But at the same time, there's another thrust in my group is to design a novel catalytic reactors. That is not only because we can use the reactors to deliver industrial relevant current densities and selectivity, but at the same time, by designing novel catalytic reactors, we can also help us to have a better inoperando X-ray absorption spectroscopy techniques to help us to understand better about the catalytic materials status under the operation conditions. So in today's talk, I will briefly introduce several representative examples in both catalytic material design and the reactor engineering. So first of all, the challenging part for the materials design for CO2 reduction is obvious. The biggest challenging part is that actually the CO2 is a relatively stable molecules. So you can imagine that if we want to dump electrons to CO2 molecules, there is always water molecules surrounding the CO2 because we need to have protons from water. So think about that. The water molecule can also get electrons to produce hydrogen, but that's not what we want, right? We want the electrons to go to CO2. So one of the biggest challenges is the competition of hydrogen evolution reaction. So most of the catalysts actually, if you try to test their CO2 reduction performance, most of them tends to dump electrons to water instead of the CO2, because CO2 is a relatively stable molecule. And also there is low selectivity, not only because we dump electrons to hydrogen, but also, as you can see, all the reaction pathways towards different products have very close thermodynamic potentials. So the electrons can feel free to go to different type of products. And that results in the low selectivity towards a single product. And the low activity means that if you look at these high value products like C2 or even C3 products, there are more than 10 electron transfer steps. So if there is only one electron transfer step that has a very high kinetic barrier, the overall reaction speed will be slowed down. So how to address those challenges actually relies on a better control of the catalytic material's electronic property. So let me use a very simple example here, which is the hydrogen evolution reaction to share with you guys why the electronic property of the catalytic materials actually plays the key role in determining the catalytic reaction. As you can see, the protons once goes to the surface of the catalyst, between the proton and the catalyst surface, there will be a chemical bond formed between them. So through this chemical bond, electrons can be dumped and be tunneled into these protons to generate atomic hydrogen. And these two atomic hydrogen can combine together to become the molecular hydrogen and live away from the surface. So this chemical bond actually plays a critical role here. The strength of the chemical bond is actually determined by the surface property of the catalyst. And you can think about that. If we bind the intermediates too strong, the product release process will become very slow. But if we say we want to bind the intermediates very weakly, then the electron tunneling process, the electron transfer process will become slow. So basically, in principle, our idea is to design an electrocatalyst that has a proper electronic structure that can bind your reaction intermediates, like protons here, just properly, not too strong, not too weak, so that you can deliver the maximum catalytic performance. This is true in hydrogen evolution reaction, and this is even truer, in CO2 reduction. As we can see, I usually want to use this simple example to share with you guys how the electronic property matters in CO2 reduction. Is as we can see, the platinum and gold, they only have 1d electron difference. They are neighboring in the periodic table. They have very different electronic properties. And as a result, their C.l.S, their CO2 reduction performance is completely different. As we can see, the platinum is still nowadays the best HER catalyst, the hydrogen evolution catalyst, and it never dump electrons to CO2. But for gold, its neighboring element is nowadays the state of the art, a CO2 reduction to CO catalyst. So the slightly change of the electronic properties actually results in a huge change in their catalytic performance. But if we move our attentions away from these noble metals, but goes to these low-cost transition metals, like iron, nickel, cobalt, and so on, at the very beginning, dates back to 5 years ago, people really pick up those nickel, cobalt, iron, those low-cost transition metals as good candidates for CO2 reduction, mainly because of two reasons. Number one is they are generally very good HER catalysts, so they generate hydrogen very actively. So you don't want to start with the materials that has a lot of competitions in the HER side. And the second problem is, even though you can reduce some of the CO2 to become a CO molecule on the surface, as we generally know that those transition metals can be easily poisoned by CO, like human beings. If we breathe in CO into our blood, the iron species in our blood can bind CO2 strongly and oxygen cannot exchange, right? This is the same thing happening on the surface of the catalyst. But at that time, when I started my group, we don't trust this theories. We just want to say, hey, why don't we try it? Why don't we use our experiment to see what's really happening? So we started with the nickel metal surface. We test them in the C.l.S conditions. As you can see, most of the electrons, exclusively 100% of the electrons goes to hydrogen, and nearly non-electrons goes to the CO molecules. So that actually reflects the past series are correct. But at that time, our idea is, if we can further shrink the size of nickel nanoparticles all the way down to single atom catalyst. The term here we refer single atom catalyst is not like an isolated atom that is floating around in air or so. We are referring to separating the atoms, the nickel metal atoms, into isolated spots where we can use graphene defects to confine them into different locations. So there will not be any nickel-nickel direct interaction. So we can change that electronic property from a continuous metallic band structure to a discrete band. Maybe it will be a very complicated band structure, but that significant change in the electronic property at that time, our intuition is, might give us an opportunity to turn these non-active materials into very active materials. So we collaborate with theoretical simulation groups, Jens Noskov, to try to use simulation to see if this idea really makes sense. So we test the nickel single atoms, we dope the nickel single atoms in the graphene defects, different type of defects, and we try to tune different coordination, like if you have a 1 nitrogen coordination, 4 nitrogen coordination, and so on. And we try to simulate each of the elementary steps, starting from the CO2 absorption, CO2 activation, CO formation, and CO desorption. As we can see from this thermodynamic chart, free energy gives free energy chart. As we can see that if we look at the nickel metal first, the CO2 activation step is relatively low on the nickel surface. But once the CO formed on the surface, the desorption becomes very difficult. As you can see, this thermodynamic sink that binds the CO2 strongly. So that is agrees well with our previous prediction. But if you look at these nickel single atoms, nickel single atomic site, even though the first CO2 activation barrier is slightly higher than the nickel metal, which can be offset by applying more negative overpotentials, but the CO desorption becomes much better. So that gives us a great confidence this type of nickel single atomic site might be a very promising site for us to reduce CO2 to CO. So at that time, we were thinking to controllably synthesize the nickel single atoms. But at that time, we don't have that experience to make that happen. So what we want to do is try to mix every precursors together and use an electrospin technology to spin out those carbon nanofibers and do the annealing process. As you can see, we have these carbon nanofibers formed, embedded in which we have a lot of the black dots. And if you zoom into that black dots, those are actually nickel nanoparticles. But there is a very unique core shell structure here. As you can see, the nickel nanoparticle is tightly surrounded by a few layers of graphene. And that actually provides us a great opportunity to see is, number one, is those nickel nanoparticles are not the wanted ones, because we don't want nickel nanoparticles to generate hydrogen, right? But the good thing is those graphene shells will be tightly surrounding the nickel nanoparticle to block the direct contact between the particle and water, so the hydrogen evolution can be blocked. And also during the synthetic process of the graphene, if we intentionally introduce some defects, we might be able to trap a lot of nickel atoms in the graphene shell regions where the reactions can happen. So then we ask ourselves several questions. Number one is whether there are indeed nickel atoms trapped in the graphene areas. Number two is if we did have found out there are some of the nickel atoms trapped there, are they single atoms or they are in cluster form, right? And the third one is even though if they are in single atoms, what is their coordination structure? So those questions are getting more and more challenging. But the first one is relatively simple for us to answer. We can use the TEM mapping technology, the EDX mapping. So we can see the nickel signals coming from the nickel nanoparticles are very intense in these region areas. But away from that, into the carbon-rich areas, we do still see a lot of the nickel signals. So that actually gives us the confidence that we indeed trap a lot of nickel atoms in the carbon areas, in the graphene areas. And then comes to the second question, whether they are in clusters or in single atomic sites. This is a very difficult question at that time for us to answer. Usually, people will use the X-ray absorption spectroscopy and do a Fourier transfer to get the exhaust spectrums, where we can differentiate the nickel-nickel bond, which is sitting about 2.2 angstrom or so. And if it's a single atom, it might only have the nickel carbon or nickel nitrogen bond that has a very much shorter bond distance, that is about 1.5 angstrom. So using the c.l.s, we can differentiate that. So we collaborate with Dr. Yongfeng Hu from C.l.s. That is our initial collaboration, dates back to 2016 or 17 or so. But we realized that this powerful technology might not be, might not be able to provide us a direct evidence to demonstrate our idea. It is because in this core shell structure, we find a very difficult time to get rid of these nickel nanoparticles, because our sample will always have these nickel nanoparticles tightly embedded into the carbon matrix. Even we use very strong acids, try to leach them out. No, there's no chance to get them out because of the graphene is so tightly surrounding them. So as a result, you see that from the XAS, we still get a dominated signal from the nickel-nickel interaction. And compared to the nickel foil, there's only a small shoulder peak. That gives us a sense that there might be a lot of the nickel carbon and nickel nitrogen bond, but this is not a direct evidence for us to claim this idea. Then we utilize a different technology which is called atom probe tomography by using a very high voltage electric field between the sample tip and the two-dimensional mass spec. And by shining the lasers frequently, we can evaporate the atoms, each of the atoms, out of these sample tips, so that we can collect the signal from the two-dimensional mass spec and then reconstruct them back into a three-dimensional tomography. So if you look at this sample tip, as you can see, this is a tomography. As we can see, each of the pixels represent one atoms, and the red is carbon, green is nickel, and blue are nitrogen atoms. And if you zoom into carbon-rich areas, as you can see, we can clearly resolute the graphene layer structures. But if you look at this top view, we have direct evidence that the green dots are the nickel atoms are isolated doping in the carbon matrix. The good thing is we only have one nickel atom that potentially have a direct coordination with nitrogen atoms, but most of them are directly coordinated in the graphene defects. So this is slightly different from previous people's perspective that most of the nickel single atoms will be coordinated with nitrogen. But in our case, most of them are coordinated just in carbon defects. And then we feel confident that there are a lot of the nickel single atoms in the graphene area. So we test our sample. And as a result, very promising result is, as you can see, with more and more negative potentials applied, we do see a CO selectivity slowly jump to more than 90%, and the hydrogen evolution gradually suppressed to less than 10%. So by tuning the structure of a nickel catalyst from a nanoparticle to a single atomic site, we can completely flip over the preferred reaction pathway. As you can see from these nickel nanoparticles, they get 100% of hydrogen, but in the nickel single atoms, we get more than 90% of CO out of CO2 reduction, and the stability is also very promising. And after catalysis, this core shell structure is still there. And a natural question to that, a follow-up question to that is simple: is why we still need to keep these nickel nanoparticles here? Because we now understand it won't participate into the reaction. Only the surface nickel single atoms is participating into the reaction. So the second project that we're doing is trying to get rid of these nickel nanoparticles. And we just directly start with graphene nanosheets, where we have a lot of defects pre-created, and then we spray coat trace amount of nickel atom precursors, and we do a thermal annealing, and those nickel atoms can be automatically sucked into the defects to form these atomic sites without direct nickel-nickel coordination. And this becomes a much better materials platform for us to use the X-ray absorption spectroscopy to understand better about its coordination structure. As you can see from here, the pre-edge actually showed us the nickel single atomic has an oxidation state that is sitting between the nickel oxide and the nickel metal. And if you do the Fourier transfer from the extended edge, as you can see, the dominated signal now actually comes from the nickel-carbon or nickel-nitrogen coordination. There is no direct evidence that there is nickel-nickel bonds sitting there. So no nickel clusters can be seen using the XAS from these nanosheet materials. And if we test their CO2 reduction performance, this is even better than the previous version. As you can see, we have much wider electrochemical window to get more than 95% of selectivity. But if I'm trying to normalize them back to the active sites, actually both of the catalysts, even though in different morphologies, they share quite similar turnover frequencies, which means that even though their morphologies are different, but their active sites are the same. Those are the nickel single atomic sites. And our third idea, let me try to make sure the time is still on track. So the third idea is now we get a very deep understanding of the active site, which is the nickel single atoms for the CO2 reduction. How about further scaling up the materials for futures, large-scale productions, as well as the current density? So two ways. Number one is the graphene substrate is still, even though it's very effective, but it's still very expensive. So how about if we can translate those single atom sites from the graphene nanosheets to very low cost carbon blacks? So the carbon black substrate is thousands of times cheaper than the graphene and can be easily large scale produced. Then we can realize a large scale production and low cost production of those single atom catalysts. So we did the same thing. We dig holes in the carbon black. We disperse trace amount of nickel atoms and do the annealing. As we can see from this carbon black substrate, we still get isolated nickel single atoms without a problem. And now we can get gram scales from one batch of synthesis, different from the previous graphene substrate. We only get milligram scales of catalyst. And the second step to scale up this process is the current density. In most of the previous studies in CO2 reduction, people generally used this type of H cell. So basically what we do is we have the catalyst electrode, we merge that in the water, and we bubble that water with CO2. So basically the CO2 get reduced on the surface of the catalyst are the CO2 molecules that is dissolved in water. So imagine that concentration compared to the water, you might get more than 99.99% of surrounding molecules are water, and only trace amount of molecules are CO2. So that actually gives us a limitation of the current density, because it won't be limited by your kinetics, but later on it will be limited by mass transport of your CO2 from the bulk electrolyte to the surface of your catalyst if you deplete the surface CO2 molecules. As we can see, the current densities are always saturated about 10 milliamp per centimeter square or so. But based on our experience in the previous few cell studies, now we want to flip over the concentrations of CO2 and water. So in this case, we're using a membrane electrode assembly. And now we can purge in high purity of CO2 gas. And of course, it needs to be humidified because we need to have the water molecules to provide the protons. But in that case, we can provide more than 95% of the concentration that is coming from CO2. And this is in a gas-phase reaction, so that you won't be limited by the mass transport of CO2. And this is an important part of the cell engineering. And as a result, as you can see, if we are using the exact same type of catalyst, but different type of reactors, we can see the current density can be 1 order of magnitude improved. But our selectivity of CO can be maintained more than 98%. This is a much improved scenario compared to the traditional H cell reactor. And based on that, both the scaling up of the current density as well as the scaling up of the single atom catalyst, we make this MEA cell that is about 10 centimeter square, 10 centimeter by 10 centimeter, that's 100 centimeter square, about this size. And we can now deliver amp scale of CO2 reduction current. And we do the calculation. This is about 3 to 4 liter per hour CO production rate. And if you want to deliver a high rate of CO, you can simply stack the unit cells into the capacity that you want. And we can make a very small sub-conclusion. These three works actually reflect some of the style of our group's research. We start with a very complicated structure of materials by using different type of advanced characterization tools, atom probe tomography, X-ray absorption spectroscopy. We slowly review what's really happening on the surface, what's the real active sites. And then we simplify the design of the catalyst and only magnify the active sites. And then we also want to lower the cost of the material synthesis and also engineer the cell design for better performance. Like what I mentioned in the beginning of the slides, we do see there is another attractive product, which is the formic acid. This is also a 2-electron transfer to CO2, but different from carbon monoxide. This is a liquid product. So as we can see from the performance metrics, the formic acid can also be a targeting liquid fuse for us to produce from CO2. But the problem for this TA analysis is they didn't consider the product separation process, the product separation cost. That might be overwhelmingly high if you in a real production scenario. So what does that mean? In a traditional electrolyzer, also the same in the CO2 reduction electrolyzers, we will always need to use the liquid electrolyte sitting in between the cathode and the anode. There are basically two functions for the for the liquid electrolyte. Number one is it maintains good ionic conductivity, so the electricity can pass through the whole cell very efficiently. And the second function is it can function as a liquid collection beds. So once you have the CO2 get reduced to become the formic acid, this formic acid liquid will be collected by this liquid electrolyte. So that actually creates a challenge. It's because all your products, all your formic acid products will always be in a mixture with your liquid electrolyte. You have a lot of the potassium ions, you have bicarbonate ions, you might have sodium ions, you might have chloride ions. This will need to be separated as a downstream separation process. And that will, like what I said, will add a lot of additional cost and energy cost to your product. So at the very beginning, our motivation is simple. If we can design a novel cell that can directly help us to directly produce high purity of formic acid without the mixer process, then we can probably lower down the cost of production by a lot. So with that idea, with that motivation bear in mind, we borrowed a lot of the idea from the solid state electrolyte in the lithium-ion battery field. If we can make a porous solid electrolyte layer between the cathode and anode, we might be able to solve the product mixture problem, which is because the solid electrolyte can still maintain very good ionic conductivity between the cathode and anode, but at the same time, it won't be able to dissolve in water. So once the formic acid is produced and crossed the anion exchange membrane into the middle layer, solid electrolyte layer, by slowly flow the deionized water, we can easily grab out those generated formic acid without the mixture with impurity ions. So by doing so, we utilize a two-dimensional bismuth catalyst as a representative example to generate the formic acid. And as you can see, using the proton conductors, which is the solid electrolyte conductors, we can get more than 90% of formic acid selectivity. So that guarantees a very good catalytic activity. And this is the picture of our cell, cathode, anode, and sitting in between, there is a porous layer of solid electrolyte. And also, it's very obvious if you're slowing down the DI water stream, but maintaining the formic acid generation rate, we can accumulate very high concentration of high purity formic acid. As you can see, we can get up to 30% of formic acid in its very high pure form. And long-term stability also works very well. As you can see, these pure formic acid solutions collected from our long-term stability test that can be directly used for downstream applications. Due to the limited amount of time, I might just skip these few slides, but I want really to show you guys a new concept of using the solid light device. So with the successful development of this solid electrolyte reactor in the CO2 reduction part, we can also use the same concept to another electrochemical synthesis, which is the oxygen reduction to hydrogen peroxide. We know that during this pandemic, hydrogen peroxide can be used for disinfection purposes use, but the localized production is limited. So in this case, the oxygen can be reduced to the hydrogen peroxide molecules instead of the water in the fuel cells by designing a 2-electron selective catalyst. But in previous studies, all the hydrogen peroxide will also be mixture with the liquid electrolyte. So that cannot be directly used. So our idea is if we can utilize the solid light reactor, we probably can get high purity hydrogen peroxide out of this device. So this is the performance metrics. We can deliver very high current densities. And I want to share with you guys a simple animation that shows the highlights of this work.
Hydrogen peroxide is one of the most important chemicals in the world, with wide applications across both industry and everyday life, including paper and pulp manufacturing, chemical synthesis, and wastewater treatment, among many other uses. Hydrogen peroxide is currently manufactured in centralized large-scale chemical plants through an anthracnone cycling process that consumes fossil fuels, emits carbon dioxide, and produces many organic wastes. Currently, researchers are trying to produce this important chemical compound in a green and delocalized manner with the input of just sunlight, air, and water. To do this, solar energy is converted into electricity, which drives an electrochemical reaction that converts oxygen and water into hydrogen peroxide with the help of suitable catalysts. In a typical electrochemical reactor, on the surface of one electrode, oxygen is reduced to HO2 minus ions, and on the surface of the other electrode, water is oxidized to oxygen, which releases protons to form the compound. Unfortunately, the hydrogen peroxide generated using liquid electrolyte is mixed with other ions, so it cannot be directly used in many on-site applications. Now, the CAT group at Rice University has successfully addressed this challenge by developing an electrolyzer that uses a solid electrolyte to continuously produce hydrogen peroxide solution without involving any impurities. This porous solid electrolyte layer can efficiently transport ions, just as the liquid electrolyte does, but does not dissolve in water so as not to introduce any ionic impurities into the generated products. Using this solid electrolyte design, the CAT group demonstrated the production of hydrogen peroxide solutions with high concentrations of up to 20% hydrogen peroxide by weight. To demonstrate a potential application in water treatment, the group directly mixed the pure hydrogen peroxide solution produced from their electrolyzer with collected rainwater. The organic contaminants in rainwater were successfully reduced to below the requirements for drinking water standards, leading towards a potential solution to help people anywhere in the world who do not have access to clean drinking water. This technology could change the game and pave the way for advancements in green, sustainable, and delocalized chemical synthesis.
Yes, An interesting story to share here in this experiment is we actually collected the rainwater from the rice campers. We tested the total carbon contents in it. We call that TOC, which is the small organic carbon molecules in the rainwater. That's about 5 ppm. And we checked the handbook from the Texas drinking water standard. That needs to be below 2 ppm. So I told my student, no, you never want to drink the rainwater from Houston areas because we have so many chemical plants surrounding us. And then we add a little bit of the hydrogen peroxide inside the rainwater that can be completely removed. So that can be a very effective way for us to produce drinking water from rainwater if there is still some contaminants in it. So with that, I would like to make a conclusion of my talk. Basically, in my group's research, we are focusing on the 4 basic elements that like what I mentioned at the beginning, carbon, oxygen, hydrogen, and nitrogen. So in today, I only mentioned a little bit of the representative examples, but hopefully in the future, we'll have more opportunities to exchange the ideas here. But for carbon, we mainly focus on the CO2 reduction and carbon capture. Oxygen, we reduce oxygen to hydrogen peroxide. That's one of the major focus right now for us. And hydrogen, as you know, we split water to clean hydrogen using renewable electricity. And nitrogen, we want to convert waste nitrate to ammonia. So all of these chemical conversions are happening using the electrochemistry, using renewable electrons. And also, I would like to take this opportunity to express my, great gratitude to the, beamline scientists, Dr. Yongfeng Hu, Morrison, Graham, all of my, strong collaborators and close collaborators without whose support, this won't be successful. And over the past several years, as you can see, our collaboration is very effectively starting from 2017, and we still have 2 to 3 works are going on, if I remember correctly, with Morrison and Graham. And with that, I would like to take questions, and I'm looking forward to our future collaborations.